Lab 5, Create Your Own Adventure by Madeline Gaffney. The topic I chose to observe for Lab 5 was conservation of momentum in collisions, specifically the collision of two pool balls. In this lab, I observed the motion of a collision, analyzed the motion, and used the data I found from Tracker to create a model in VPython, which would predict the motion of the collision in a computational model. The objective of the lab was to determine if the collision followed the principle of conservation of momentum by observing the experimental and computational motion. My conclusion was that while the computational model displays the conservation of momentum principle very accurately, the actual collision does not, because in reality, there is no perfectly elastic collision due to the impact of external forces. The main conceptual component of this lab is conservation of momentum. We know that the initial momentum is equal to the final momentum, as seen in the first equation. I incorporated net force in my code because it is equal to the change in momentum over change in time. The energy principle was needed in order to calculate the system energies and changes in energy for my computational model, so I made use of the kinetic and potential energy equations. Lastly, I used Newton's second law to update the positions of the pool balls as the code iterated. Here is the video of the collision I observed. I uploaded the video to Tracker. Here, I set up an XY axis with the origin at the center of the red pool ball, which is initially at rest, and I set the calibration stick equal to the diameter of the red pool ball. I then used the center of mass tracking device to track the motion of the collision. I tracked the blue ball first, and its position time graph can be seen in the top right corner. Then I tracked the motion of the red ball, whose position time graph is in turquoise in the top right corner. From this point on, I will refer to the blue ball as ball A and the red ball as ball B. I used the data that I found in Tracker in order to initialize my computational model. The mass of a standard pool ball is approximately 0.16 kilograms, so ball A and ball B have the same mass. The initial time of observation is at 0 seconds. Ball A's initial position is at negative 0.058 meters, and ball B's initial position is at the origin. Ball A has an initial velocity of 0.127 meters per second, which was calculated using Newton's second law, and ball B is initially at rest. From the initializations and physics concepts discussed, I composed this code. After setting up the visual aspect of the computational model, I inserted the data and initializations, such as each ball's mass, the initial time, the change in time, ball A's initial velocity, ball B's initial momentum, which is 0 due to its initial velocity of 0, and the final and initial momentum of ball A. I also defined gravity as 9.8 meters per second squared. I inserted the energy principle by making use of the equations to calculate kinetic and potential energy using ball A's mass, velocity, and position. All of these values and equations are defined initially so that they can be used in the calculation loop. I used a while loop that would allow the code to iterate until the motion of the collision was completely through, which occurs as t approaches 0.3 seconds. I used Newton's second law to update each ball's position throughout the collision. I updated the time so that the while loop would correctly iterate until 0.3 seconds, and I updated each ball's momentum using an if statement. I then calculated the energy changes with the knowledge that the change in energy is equal to final energy minus initial energy, which I defined prior to the calculation loop. Lastly, I used the energy changes calculated in order to plot the graph. The final velocity of each ball is printed in the Python shell. When I run the module, a window appears with the blue and red ball. The blue ball starts with non-zero velocity in the positive x direction, strikes the red ball, and quickly slows to a stop. The red ball, initially at 0 velocity, then picks up speed in the same direction. The graph then zooms out, and the trails of each ball's motion, as well as their stopping positions, are visible. While the blue ball in the original video continues moving for a few seconds after striking the red ball, the blue ball in the computational model stops almost immediately after striking the red ball. In conclusion, the motion as shown in the computational model acts according to the conservation of momentum principle because the blue ball stops after striking the red ball, and it transfers all of its energy to the red ball. The experimental model, or real video, does not act completely in accordance with the conservation of momentum principle because the blue ball continues moving after striking the red ball when it should stop. Energy was not conserved in this collision, and it can be observed that real-world collisions are never perfectly elastic, and therefore momentum is not completely conserved as it is in a computational model.